Welcome to Ask and Learn.
Okay, this problem is asking us to predict the product of each of these reactions. Okay, so the way that they formatted this, it's basically my compound with a step 1 and step 2 of synthesis. Okay, so basically my molecule, and that is going to be reaction with step 1 and step 2. Okay, so if we're not used to that format, this is the format that we might be more used to. Okay, but with that in mind, let's go ahead and perform these reactions. So first up, I have diethyl heptane dioate. Okay, because that is the compound name, I'm going to start off with the very back and then work my way from right to left. Okay, so dioate, that means I'm going to have 2 esters on my heptane. So that's going to be 2 esters on my 7 carbon chain. So let's go ahead and write that out. 7 carbons, just like that. And then on the first and the last carbon, I'm going to have the connection to my ester. Okay, and I know it's going to be on the first and 7th carbon, simply because if they weren't on those first and 7th carbons, then we would have ketones. Okay, so those are the structures of my ester so far, but I need to know what is going to be attached to these oxygens. Okay, and that is going to be diethyl. So that means I'm going to have 2 carbons attached to each of those ether-like oxygens. So I'm going to have my ethyl and my other ethyl, diethyl. Okay, that is the structure of heptane dioate, and now let's go ahead and perform my reaction. Okay, first up we have sodium ethoxide. So sodium ethoxide is going to behave as a base, and that is going to take off the most acidic hydrogen. Okay, so if we analyze this compound, again we have these esters, we have an alpha carbon here, and we also have an alpha carbon there. Okay, each of those are going to have acidic protons, and those are the ones that are going to get deprotonated by my sodium ethoxide. Okay, but because this molecule is symmetrical, we only have to focus on one of those hydrogens. So let's just take off this one, for example. Okay, so sodium ethoxide is going to take off that proton, meaning I'm going to have to move the electrons from this carbon-hydrogen bond onto this carbon. Okay, so that will result in the following compound. I'm going to have my ester on this side, and then my 7 carbons, just like that. And then over here on this carbon, we deprotonated it, so it has that nucleophilic carbon. Okay, so now that nucleophilic carbon can behave as a nucleophile to attack an electrophilic site. Okay, this is going to perform a Dieckmann condensation, otherwise known as an intramolecular Claisen condensation. Okay, and that is because we have this nucleophilic carbon, and we already have an ester on the same molecule. Okay, intramolecular condensations are going to happen before even intermolecular condensations. Okay, so the electrons from this carbon are going to travel all the way to this carbonyl, moving the electrons up to that oxygen. Okay, and that is going to make a 1, 2, 3, 4, 5, 6 membered ring. Okay, I always label my nucleophile as carbon number 1, and then my electrophile, the site that the nucleophile attacks, is carbon number 6. Okay, or at least the last number. Okay, so the first thing I'm going to do is write out my 6 membered ring, like this, in which this is carbon number 1, 2, 3, 4, 5, 6. Okay, so attached to carbon number 1, right here, we have the connection to this ester. So I'm going to attach that directly to my carbon number 1. Okay, just like that. Okay, if we analyze carbon number 2, we don't have anything of importance aside from carbon number 1 and carbon number 3, but we already represented that on my cyclic structure. Okay, so we don't have to write anything else. Okay, and then we do have those hydrogens attached to it, but again, in skeletal structures, we don't have to write that out. Okay, carbon number 3, same thing. We just have those hydrogens. 4, same thing. 5, same thing. But then 6 is going to be where it gets a little bit interesting, because we have that oxygen with the now negative charge, and then I have the presence of this ether-like oxygen with its diethyl group, or that ethyl group. So I'm going to have the oxygen with its ethyl group. Okay, so again, this is a Dieckmann condensation, otherwise known as an intramolecular condensation, in which we move the electrons down from this oxygen to recreate my double bond. And in the process of doing that, I'm going to have to get rid of a leaving group. And that leaving group is going to be this ethoxide. So the product of that is going to be as follows. I'm going to have my 6-membered ring, like that. On this first carbon, I have my ester. And then on the carbon right next to it, I'm going to have the presence of my carbonyl. Okay, and that carbonyl originated from the movement of electrons down from the oxygen to recreate my double bond. Okay, and then we did have to get rid of ethoxide, so that is going to be present in the solution as well. Okay, so ethoxide, very similar to how it behaved as a base in the first reaction, in the first step, is going to behave as a base in this component of the reaction as well. Because, again, this is a base, and we still have an acidic proton. That acidic proton is right here. Okay, so using this base, I'm going to take off that proton, simply because that proton is acidic, and that is because it's sandwiched between these 2 carbonyls, making it particularly more acidic. Okay, so after I take off that proton, I'm going to have to move the electrons between that carbon-hydrogen onto this carbon right there. Okay, so that is going to yield this product, in which I have my 6-membered ring, And it's basically going to be the same thing as before, except for the fact that I have those lone pairs present on this center carbon. Okay, so that is the final reaction after step 1. That's the final product. Okay, but again, we don't have just step 1, we have step 2, and that is going to be HCl. So HCl, all it's going to do is simply protonate this basic carbon. So I have HCl. I'm going to use these electrons to attack that H, the hydrogen, and protonate that site. So my final product is going to be this. Okay, where I simply have the hydrogen there, but we don't have to represent that simply because in skeletal structures we don't have to show that extra hydrogen. Okay, so that will be my final product. And now let's move on to this second one. Okay, so for the second one, we have pentanoic acid, reaction with PBr3, Br2, and that's going to be followed up with hydrolysis. Okay, so let's go ahead and write out our pentanoic acid. That's going to be 5 carbons, and then oic acid corresponds to a carboxylic acid. So similar to the ester problem, the diethyl heptane dioate, we know that carboxylic acid is going to be present on the either first or last carbon, simply because if it wasn't, at that point it wouldn't be a carboxylic acid anymore. Okay, so I have my 1, 2, 3, 4, 5 carbons. Let's just put it on this last carbon right here. So there is my carboxylic acid. Okay, that is pentanoic acid. Okay, so we're going to react this with PBr3, Br2, and that is going to undergo hydrolysis. Okay, so these reagents correspond to the HVZ mechanism. That is Hell-Volhart-Zielinski. Okay, and what that does is essentially retain my carboxylic acid, but it places a bromine on this alpha carbon. Okay, so the product of that is going to be this. 5 carbons, carboxylic acid, and then I have my bromine on that position. Okay, if you're curious about the mechanism, it's in the textbook, but basically what we do is we create an acyl bromide, and then from that acyl bromide, we go ahead and brominate this alpha carbon, and then after that, the purpose of hydrolysis is to reform my carboxylic acid from that acyl bromide. Okay, so that is going to be the final product. Okay, next up we have acetone reacting with LDA/THF, in which THF is simply just a solvent, and then we're going to have a step 1 of slow addition of ethyl acetate and a step 2 of HCl. Okay, so let's go ahead and try this out. So acetone, I'm going to have this compound, basically just a ketone. Okay, and that is going to react with LDA. So the purpose of having LDA as opposed to something like sodium hydroxide, for example, is that LDA is a super strong non-nucleophilic base. Okay, what it's going to do is it's going to deprotonate every single one of these acetones. Okay, so again, I have my very strong base of LDA. That's going to take off this acidic proton, moving the electrons onto that carbon. Okay, so sodium hydroxide, it would also deprotonate that alpha carbon, but we're going to have a mixture of products because we're going to have a mixture of deprotonated acetones and a mixture of non-deprotonated acetones. Okay, and then that would be prone to a potential self-aldol condensation. Okay, and we want to avoid that because we have the addition of these 2 other compounds. So that base is going to deprotonate every single one of these molecules, and that is going to essentially avoid the self-aldol condensation. Okay, so I'm going to get this as my product of that, in which I have my deprotonated acetone. Okay, so after that, I'm going to have a slow addition of ethyl acetate. Okay, so ethyl acetate is going to look like this. I'm going to have my, I recognize 8 as corresponding to an ester. So I'm going to write down the basic ester compound. Okay, and then acetate, that corresponds to just a CH3 on this side, and then the ethyl corresponds to whatever is attached to my oxygen. So that's going to be 2 carbons attached to that oxygen. Okay, so that is ethyl acetate. And the reason that we add it slowly is because we want to avoid the deprotonation of this carbon. Okay, instead we want to just perform my glycine condensation, in which this nucleophilic carbon from my deprotonated acetone attacks directly this carbonyl. Okay, and again, we want to avoid the deprotonation of that alpha carbon. Okay, so after I attack that electrophilic site of the carbonyl of my ethyl acetate, I'm going to have to move the electrons up to this oxygen, and that is going to result in this compound, in which I have my acetone, and connected to this carbon, which was my nucleophile in the previous step, that is going to be connected to this new carbon, which was the carbonyl in my previously formed ethyl acetate, and then connected to that carbon, we have the presence of my oxygen with a negative charge, my ethyl group, my ethoxide group, and then my methyl group. Okay, so again, this is a glycine condensation in which we're going to have to move the electrons down from the oxygen onto this single bond to make a double bond. And in the process of doing that, I'm going to have to make my ethoxide into a leaving group. Okay, so the product of that will be as follows. I'll have my acetone structure, and then on the beta carbon, I have my presence of my other ketone. Okay, so that is the structure so far. But again, because we had to get rid of ethoxide in that step as a leaving group, that ethoxide is going to behave as a base. And that base is going to deprotonate this alpha hydrogen. Okay, and it's going to have to move the electrons up to that carbon to make a nucleophilic / basic site. Okay, just like this, lone pairs on that central carbon. Okay, so the purpose of HCl is to basically just protonate that site. Okay, so we're already done with step 1, and we can just go ahead and react it with HCl to protonate that basic carbon. Okay, so using HCl, a very strong acid, I'm going to protonate that basic carbon. Okay, and that's going to form my final product of this compound. Okay, so that's number 3. Now let's move on to number 4, or part D. Okay, so this is diethyl 2-ethyl hexane dioate reaction with sodium ethoxide and HCl. Okay, so right here I recognize that I have dioate. That means I'm going to have 2 esters, and then the hexane corresponds to a 6-carbon compound. The 2-ethyl corresponds to an ethyl group on the second carbon, and then the diethyl corresponds to the presence of 2 ethyl groups on my oxygens of my ether, like oxygens of that ester group. Okay, so breaking it down again, dioate on my 6-carbon compound. So let's draw out that 6-carbon compound first. 1, 2, 3, 4, 5, 6. Here I have my esters on my first and last carbons. Okay, that is the basic structure of my hexane dioate so far, but I still have to add this diethyl group, and I still have to add this 2-ethyl. So that 2-ethyl is going to correspond to the presence of an ethyl group on the second carbon of this 6-carbon chain. So I have 1, 2, 3, 4, 5, 6 carbons on that second carbon right there. I'm going to have the presence of an ethyl group. So 1, 2 carbons. Okay, and then diethyl just corresponds to the presence of 2 ethyl groups on each of my oxygens. So right here, 1 ethyl group, 2 ethyl groups. Okay, diethyl. Okay, so that is the structure of my diethyl 2-ethyl hexane dioate. Now let's go ahead and react it with sodium ethoxide. Okay, so this sodium ethoxide is going to look like this. I'm going to have my basic ethoxide. Okay, so that ethoxide is going to have a choice. It can either deprotonate this alpha carbon, or it can deprotonate this alpha carbon. Okay, the question is, which one is it going to deprotonate? Okay, and the answer of that lies in the previous problems that we've done before. So as we look at this example of a glycine condensation, we had to deprotonate with our base this alpha carbon, right? This alpha carbon here that had the loss of 1 hydrogen. Okay, and if we move along, we have that same alpha carbon here. Okay, moving on still, we have that alpha carbon over here. Okay, and still only the 1 deprotonation. And if we keep moving along, we have the next deprotonation. So as we can see, we have 2 deprotonations of that alpha carbon. Okay, and if we even move up to the first one, again, we have this loss of proton in that alpha carbon. And if we keep moving along, we have the eventual loss of that same proton off that alpha carbon once again. Okay, so in glycine condensations, we have to have the loss of 2 protons. Okay, that's just the part of the mechanism. So if we analyze this compound, we can see that we have my alpha carbons here, and we have an alpha carbon here. Okay, but we're trying to question which is the one that we're going to deprotonate. We're going to deprotonate this one, and that is because this carbon right here only has the 1 extra hydrogen. Okay, again, this has to have the deprotonation of 2 hydrogens. So just based on the fact that this carbon has 2 hydrogens, I'm going to have to deprotonate that one. Okay, so let's go ahead and try that one out. So I have my hydrogen, I'm going to deprotonate it with my ethoxide, and I'm going to have to move the electrons up to this carbon. Okay, so the result of that will be as follows. I'll have my 6-carbon compound. Okay, I'll have my 2 esters on each side. Okay, ethyl group right here as well. Okay, and then I still have my ethyl group on that second carbon, but I have the deprotonated carbon on that side. Okay, so similar to the first problem, this is going to undergo a Dieckmann condensation, an intramolecular glycine condensation. And that is because on this carbon, that is a nucleophilic site, I have an electrophilic site only right there. Okay, so this is going to avoid a intermolecular glycine condensation simply because we already have an electrophilic carbon on that same molecule. Okay, so if I were to perform a Dieckmann condensation, I would have a 1, 2, 3, 4, 5, the formation of a 5-membered ring. Okay, and that's simply because this carbon nucleophile is only 5 carbons away from this carbonyl, that electrophilic site. Okay, so with that in mind, let's go ahead and perform that ring closure. So I'm going to attack that electrophilic site, and I'm going to have to move the electrons up to the oxygen. So again, in terms of numbering this, I have a 1, 2, 3, 4, 5 membered ring. Okay, so that's going to form this compound. I'm going to have a cyclopentane, just for now. This is step number 1, this is 2, 3, 4, and 5. Okay, attached to carbon number 1, we have the presence of this ester group. So let's go ahead and write that out. Over here, I have my ester. Okay, carbon number 2 now. Carbon number 2 has nothing. Okay, only the attachment to carbon number 3 and carbon number 1, which is already represented in my cyclopentane. Okay, it also has those 2 hydrogens, but we don't have to represent that in a skeletal structure. Okay, carbon number 3, same thing as carbon number 2. But carbon number 4, it does have the presence of that ethyl group. So let's go ahead and write that out. Ethyl group, 2 carbons. Okay, moving on to carbon number 5. This is where it gets interesting because we have that carbon is connected to an oxygen and an ethoxide. So that oxygen is going to have a negative charge, like that, and then my ethoxide is going to be on that same carbon. Okay, so that is the structure of my molecule so far, but this is going to undergo more of the reaction steps, and that's because I'm going to move the electrons down from this oxygen to make a double bonded oxygen to that carbon, and I'm going to have to make my ethoxide leave as a leaving group, just like that. Okay, so that's going to form this compound, in which I have my cyclopentane, my ester over here, and then I have my carbonyl right there, and we can't forget about my ethyl group on that 4th carbon. Okay, so that's the structure of it so far, but again, we did have to get rid of ethoxide in that previous step. That ethoxide is going to behave as a base. Okay, so remember how we had to have the overall deprotonation of 2 hydrogens on that alpha carbon? That's where the second hydrogen deprotonation comes in. So right here, I have that same hydrogen on that same alpha carbon that we deprotonated in the first step. I'm going to take that one off. Okay, and as I do that, I'm going to have to move the electrons onto that carbon. Okay, so as I do that, I will form this as my product, in which I have my cyclopentane, basically the same thing as before, the only difference being that I have a set of lone pairs on that alpha carbon. Okay, so just like that. Okay, and again, the purpose of HCl is simply to protonate that. So using HCl, I'm going to go ahead and protonate that nucleophilic site / basic site and end up with my final product of basically the same exact thing as before. The only difference being that I have my hydrogen there now. Okay, just like that. Okay, so now we're going to move on to this 5th one. Okay, so this one we have diethyl malonate. Okay, so malonate, we might be able to recognize that from malonate ester synthesis. Okay, so diethyl malonate is going to be looking like the same thing, in which I have my carbonyl, and then I have the presence of this middle alpha carbon. Okay, and because this is malonate, it's going to be an ester, in which I have 2 ethyl groups on each of those oxygens, just like this, and just like that. That is diethyl malonate. Okay, so if we were to react this with sodium ethoxide, as my first step, what's going to happen is the deprotonation of this very acidic proton. Okay, and that is because this hydrogen, the carbon that's attached to, is sandwiched between these 2 carbonyl groups. And the presence of those 2 carbonyl groups allow for the electrons to delocalize into those carbonyls if that proton was deprotonated. Okay, so using sodium ethoxide, I'm going to take off that acidic proton, just like that. And again, I'm going to move the electrons up to this carbon. Okay, that's going to form this compound, in which I have my diethyl malonate, just like that, but I have the lone pairs on that central carbon. Okay, now we're going to react that with isobutyl bromide. So isobutyl bromide is going to look like this. I'm going to have a bromine, and it's going to be connected to my 4 carbons in which I have a branched component. So it's going to be 1 carbon, 2 carbons, 4 carbons. So 1, 2, 3, 4. That is isobutyl bromide. Okay, so what this does is an SN2 reaction. Because I have this nucleophilic carbon, I have this alkyl bromide, I can go ahead and attack this electrophilic site, because if I were to attack that, I can get rid of bromide as a good leaving group. Okay, so that's going to form this compound, in which I have my diethyl malonate, like that, but I'm connected to my isobutyl bromide now. So just like this. Okay, I basically attached an isobutyl group to that central carbon. Okay, now we're going to react that compound with HCl and H2O and finally heat. So the purpose of this is not to protonate anything, or technically it is, but it's not in the form that we were doing in the previous steps, in which I have a set of lone pairs, because obviously we don't have any lone pairs here. Okay, but what this does, paired with water and heat, is it undergoes hydrolysis. So after hydrolysis, I'll basically transform each of these esters into carboxylic acids. Okay, that's a mechanism completed in the carboxylic acid and their derivatives chapter, but basically we just have to make these esters into carboxylic acids. So what's going to happen is it's going to transform into this. I'm going to have, instead of my ester groups, carboxylic acids, like that. Okay, and then we still have that isobutyl bromide, or isobutyl group on that central carbon. Okay, and then heat right here, that is going to perform a decarboxylation reaction. And what that does is essentially gets rid of one of these carboxylic acids in the form of carbon dioxide, and it is going to make this carbon, basically we're just going to split off this whole entire carboxylic acid part. So what that is going to form is this. We're going to get a carboxylic acid, like that, on the left side, or on the right side, doesn't matter, because we can decarboxylate any one of these, it doesn't matter. Okay, and if we get that attached to this central carbon, the alpha carbon in this case, is going to be the connection to my isobutyl, just like that. Okay, so that will be my final product. Okay, next up we have acetophenone reacting with LDA and THF, and then a first step of slow addition of diethyl carbonate, and a second step of HCl. Okay, so acetophenone is going to look like this. One, that corresponds to a ketone, phen, that corresponds to a benzene as a substituent, and then aceto just corresponds to a CH3 connected to my ketone. Okay, so I'm going to have my ketone, and then as a substituent, I'm going to have my phenyl group, so like this, and then I'm going to have the connection to my CH3. Okay, so that is acetophenone. Another way to call that is methylphenylketone. Okay, and then I'm going to react that with LDA and THF. THF is just a solvent, it's basically unreactive in this process, but basically LDA is a very strong base. It's going to take off this acidic proton off of my alpha carbon. So using my super strong base, I'm going to take off that acidic proton, moving the electrons onto that carbon. Okay, so the product of that is going to be as follows. I'll have my benzene, I'll have my carbonyl, and then my deprotonated alpha carbon. Okay, so that site is now considered to be nucleophilic. Okay, and is going to be nucleophilic towards my diethyl carbonate. Okay, so we're going to add that slowly to avoid a possible deprotonation. So diethyl carbonate is going to look like this. I'm going to have my two oxygens on either side of this carbonyl, like that, and then I'm going to have my diethyl on each of those carbons. So two ethyl groups on each of those oxygens. Okay, so that is diethyl carbonate, and now I'm going to behave my nucleophilic carbon as its nucleophile to attack that carbon. Okay, that carbon is considered to be electrophilic, and as I do that, I'm going to have to move the electrons up to that oxygen. Okay, so the product of that is going to be as follows. I'll have my benzene, unaffected, connected to my carbonyl, and that is going to be connected to this carbon is the nucleophile, for example, and then we have the connection to my electrophilic carbon, which was my carbonyl in the previous step, which is connected to my oxygen right there, and then my two ethyl groups, ethoxide groups, just like that. Okay, so similar to our other Claisen condensations, we're going to have to move the electrons down from this oxygen to make a double bonded oxygen to that carbon, and then again we're going to have to relieve this carbon of its exceeded octet, and we're going to have to move the electrons away from it onto that oxygen, onto that ethoxide as a leaving group. Okay, so the product of that is going to be as follows. I'll have my benzene, like that. I'll have my carbonyl, unaffected, and then over here I'll have my other carbonyl, and then that is going to be connected to my ethoxide. Okay, and that's going to be in the form of an ester. Okay, so that is the slow addition of diethyl carbonate, but we're not done with that first step because, again, we still have that ethoxide still present in the solution. Okay, and that is going to behave as a base to take off that acidic proton. Okay, as it does that, I'm going to have to move the electrons up to that carbon to result in this product, in which I have my benzene. Okay, and then attached to that we have my ketones with my ester on that side, and then the set of lone pairs on this central carbon. Okay, so the very last step of HCl is simply to protonate that set of lone pairs. So the product is going to look like this, in which we have my ketone over here, my ester group over here, and then again, we protonated that set of lone pairs with my very acidic acid, just like that. Okay, and it's going to have the presence of that extra proton right there. Okay, so that will be the final product, and that also, all of these will be the final products of each of these synthesis problems.